So since we didn't show these earlier, let's just look at a little video of mitosis, because, you know, I happen to love mitosis, and I think you guys will too. So let's see if this will play for us. And here we go. And there we go. We're already condensed, so we have to be in part of mitosis, right? Can't be G1 or G2. You can say, ooh, look at the sausages. Okay, so we're probably late prophase. We're trying to line up, right? The spindle apparatus has got to be attaching to the centromeres, to the kinetochores. Look at them go. Oh my gosh, they were in the middle and now they're in anaphase. Getting towards the poles, we call it telophase. And oh my gosh, look at right there. There is your cell plate. So this was a plant cell. Okay, plant cell mitosis. I love it. I hope you do too. Because it really is the best thing ever.
Oh, blimey. Nerd alert!
Yeah, I know, sorry. Can't really help myself. Just, yeah. And here we have meiosis. The chromosomes are actually colorized. They're not fake chromosomes. They just, you know, inked over them in Photoshop or whatever, so they're easier to see. So let's take a looky look. We can see chromosomes condensing. Remember, this is meiosis. Right now it's 2n equals whatever. I don't know. You can see them. Ooh, they're getting to be sausage-shaped. Right? We have the homologs are pairing up. They're trying to find each other. Attach the spindle to do that. They need to line up in the middle of the cell. Right? We're lining, we're getting lined up. We're paired, we're lining up, we're in, oh my gosh, we're in anaphase 1. Going towards the poles, telophase 1. Right, some sort of dissolution of the chromosomes. Ooh, there's the membrane right there. Now we are at N. Condensation, right? This is now, they're all just individual chromosomes with their sisters lining up in the... Oh my god, it's anaphase 2. Going to the poles, it's telophase. And look, ooh, cleavage right there. We have 4 cells each at N. Woohoo! Meiosis. I love it. I love it. I love it! And then the little movie we watched last time. Oh, no, we didn't. This is a different one. This is cleavage of the egg. So as you can see, this is mitosis again. So this is, right, after fertilization and mitosis happening. And notice how the size of the egg didn't change, or the size of the zygote didn't change. It just got a ton more cells inside of it. So let's watch it again. Shall we? I think we shall. Okay. All right, so the first mitosis, second, third, fourth. So at the very beginning, during cleavage for development, the size doesn't change. And that makes sense because this egg has no energy source. It's not connected to anything. The only energy, the only ATP, enzymes, proteins, fats, all that stuff is included in that egg. Pretty cool. And then here's the one that I was talking about that we watched in class. Let's see if my circles will go away. Maybe not. No, there they are. Sorry. I didn't erase those guys. Right, here's all the chromosomes trying to line up. That little guy over there is getting left behind. Oh my gosh, anaphase. And there we go. This guy here is the one that has Nondisjunction. That's going to do what? Give you an aneuploidy. Fascinating. I love it. Okay. So an aneuploidy, we talked a little bit about in class. The only ones that survive are these different trisomies, right? That one's Downs. That's I was going to say the most popular. The most prevalent, probably the least lethal, least disruptive. It can have lots of different penetrance and expressivity, right? So different degrees of developmental delays associated with this. These two are always pretty darn lethal and very... disruptive, or individuals who have those trisomies. Aneuploidies involving sex chromosomes have less effects, right? The XO is Turner, which isn't so bad because normally females are X bar, right? So it's still a bit of a dosage compensation problem, but much better than any of the autosomes, right? So there's lots of different sex chromosome aneuploidies, many, many more that are viable and functional than those of autosomes. So here's an example of a chromosome rearrangement that's in duplication. This is still, right, this is just 2n equals 6. So this is a chromosome structure problem, not a polyploidy or an aneuploidy. This case, it's an aneuploidy, right? We have too many chromosomes. We are supposed to have 2 of each. We have 1 extra here. It's 2n plus 1. So if your original was 2n equals 6, right, you'd write it out 2n plus 1 equals 7. You would not write 2n equals 7. Right? That's really what it is, but this points it out as to what the problem is, right, rather than some other kind of issue. And then when we look at polyploidies, right, this is a triploid, an autotriploid. The book goes into auto, allo, all different kinds of things. We're just going to deal with polyploids, any kind of polyploid, and ignore the first part, auto or allo. And in this case, right, triploid is the entire number, right? Remember the ploidy? So it's 3n equals 9. So what does that mean n equals? In this case, it's not half. It's only half if it's a 2n, right? It's 3. And how do we know that? Because 3 sets of 3 equals 9. Woohoo! Okay, so this is just another way to look at it. Variations in euploidy. This is just a figure from another book, right? They're showing us a triploid. That makes sense. If this was, right, a 2n, right here, this normal guy, right, 2 sets, 1, 2, 3, 4, 5, 6, 7, 8, right, 2n equals 8. In this case, 3 sets, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, right? 3n equals 12. 4n equals what? 16, which means what? N equals 4. Okay, so you should be able to go back and forth between these, not only just the diploids like we did in the past, but with triploids, tetraploids, octoploids, all that kind of stuff. And then again, trisomies, right, and monosomies, those are talking about the aneuploids. Okay, these are all the aneuploidies go total ploid, triploid, 3 sets of chromosomes, right? Remember the ploid or the ploidy is the sets. So you're going to use a zomie or a zomie for the aneuploids. You wouldn't want to call this monoploid because that would suggest a haploid, and it's not. It's actually a diploid missing 1 chromosome. So you have to be careful with the terminology. Just fun facts about non-disjunctions. They seem to happen in older mothers, as you can see. After the age of 35, the instance of Down syndrome or a trisomy 21 goes up pretty dramatically, but above 40, between 40 and 50, right? That would be exponential, right? That J-shaped curve. So, yeah, non-disjunction, not good. Okay, here's questions for you. Answer, what is this 2n? What is the n number? What do normal gametes look like? Right? What would this look like if it were normal? We see that it's a non-disjunction. Where is the non-disjunction? Fill out this form and then just do a screenshot and upload. Right? Let's get some points. And then the last one is, what is wrong with this figure? Why is this one not okay? Okay, figure out where there's a problem here. And fill in the correct parts and mark what the problem is. And not the non-disjunction. There's something else wrong here. Take a screenshot and upload. And then here's a table of chromosome mutations. These are all the things you should know. Okay, For the auto and allo, I'm not going to differentiate between these two, but if you see those in the homework, please do those, okay? You don't really need to know the difference, but, right, it's a polyploidy, and it's just how it comes about. So please do that. All right, do you guys have any questions before we go?
Where's the beef?
I meant questions about genetics. Anything else? No, you're okay? All right. Have a good one. Thanks for listening. All right then, I'll leave you with this.
Would the doctor care for a brandy before retiring?
No. Thank you.
Some warm milk? Perhaps?
No, thank you very much. No thanks.
Ovaltine.
Nothing. Thank you.